All right, so hopefully you looked ahead at this example because if you understand what we've done so far regarding center of mass, this should be pretty straightforward. So, and if you haven't tried it yet, maybe pause right now and give it a try. And then if you have trouble, just come back. So in this example, we have three masses, and we're given the position of each of the masses. So let's just draw what we're given here. I always like to draw a picture, so I'm just going to draw a number line. Now the first mass is at -2, so I'm just going to put 0 here, and then -2 is right here, and we have a 5 kilogram mass. Or so, sorry, 5 gram mass there. And then at 1, so I'll say that's 1, we have an 8 gram mass. So I'll draw my 8 gram mass, and then the other one is at 5. So 2, 3, 4, 5. So here's 5, and here's our 3 gram mass. All right, so calculating the center of mass is pretty straightforward. You can just use the formula now. Hopefully you understand where it came from. So we're just going to take 5 times the distance from the origin. All right, so we're just going to look at the moments around the origin and add them up. So 5 times -2 plus 8 times 1 plus 3 times 5. Okay, so that's the sum of the moments about the origin. And then we're going to divide that by the total mass. 5 plus 8 plus 3. So we get 13 out of over 16. And if we want that as a decimal, we get 0.8125. Right? And that's all there is to it. But in the real world, we aren't dealing with point masses. In the real world, we have objects where the mass is distributed, right, continuously in 3 dimensions. So, in single variable calculus, we can evaluate the center of mass as long as the density of the mass can be described in terms of a single variable. And so that's what we're going to look at next. We're going to look at some examples where we have some sort of a 3-dimensional mass where the mass is distributed continuously.